This is Irodov problem 1.33. A cannon fires two shells at different angles in rapid succession, aiming for a mid-air collision where their paths intersect. The objective is to find the exact time delay required between the first and second shot to guarantee this impact. We arrive at the solution in two stages. First, we use physical reasoning to build the coordinate equations. Then we perform the trigonometric simplification required to match the textbook's final result. Solving this requires decoupling the physical location of the collision from the moment the event actually occurs. For a collision to happen, both shells must occupy the same horizontal position, x, and the same vertical position, y, at the same instant. We will define the total flight time for the first shell as t1 and the flight time for the second shell as t2. The necessary wait time between shots is the difference between these two flight times. Delta t equals t1 minus t2. To avoid managing two times, we use the trajectory equations for both shells. Equating vertical positions, we divide by x. A trig identity converts 1 over cosine squared into 1 plus tangent squared. Rearranging isolates x, 2v0 squared over g times the sum of the tangents. By removing time from the initial calculation, we have identified the exact physical coordinates where the two paths cross. Now let us reintroduce the time variables. In kinematics, flight time is simply the horizontal distance divided by the horizontal component of velocity. We express delta t as the flight time of the first shell minus the second. Then we substitute our derived expression for x into this equation. We factor out the common constants, v0 and g, to simplify the layout of the fraction. This expression is physically complete, but it is not yet optimized. To match the textbook's answer, we must perform a final trigonometric reduction. Expanding the tangents into sine and cosine, we find a common denominator. The numerator collapses, canceling out several cosine terms. Multiplying by the conjugate creates a difference of squares. We convert these to sine squared terms, triggering the final cancellation for our simplified formula. This elegant derivation reduces a complex, chaotic two-body problem into a single, highly functional, and beautiful mathematical tool. We can now apply our numerical data: initial velocity of 250 meters per second and firing angles of 60 and 45 degrees. Inserting these values into the formula gives us sine of 15 degrees divided by the sum of the cosines, all multiplied by our velocity and gravity constants. The result is 10.94 seconds, which rounds to the textbook's answer of 11 seconds. Matching spatial coordinates allow you to fix the collision point before involving the clock. Once set, finding the time difference becomes a straightforward derivation.